What about the citation?
On the lab, it asks you to give a citation like an article you find. Doesn't matter what format.
Yeah, I don't remember asking for that, yeah.
Yeah, and the web for journal article. When you search for an article, first question, give the citation for your article.
Oh.
And summarize these two aspects.
Yeah, ACS format would be preferred.
Two things. I have to leave early today, or I can't make it to lab. I have to get my daughter. Well, I guess I could stay for like 30 minutes. I don't know if you think that's even worth it, or.
Well, actually, yeah, because today's lab is like one of the few labs that you could actually do at home.
I remember you saying that, but I wasn't sure if it just
Yeah,
fell
so I
for
could.
Tuesday.
No, it's a Thursday as well.
Okay.
So I could print out the cards for you,
Okay.
and then you can just take them home. You'll have to cut them up, but then you
Okay.
could do the lab at home.
Okay, cool. Well, and then another thing. So balancing equations for some reason is just not sitting in my brain. And I was doing it, and then I looked at the key, and I was like, okay, these are all wrong. So I was wondering if I could just hold on to this.
Yeah.
Or turn it in Tuesday, or
Yeah,
Monday to you, or over the weekend if
Yeah.
I could scan it in. Okay.
Yeah, no rush on the homework. What's going on here? What? All right, let's go ahead and get started. So, are there any questions before we begin? All right, so I did grade your quizzes, so I'll try to pass those back while y'all are quizzing in recitation. And so I wanted to go back and hit a concept. So I realized when we were talking about all this stuff, I neglected to talk about kind of the double slit experiment. And I noticed your book didn't talk about it. I was trying to search your book to see if it was in a different chapter, and I couldn't find it. So I don't know what's up with that. But so the question I got was, well, how do we know that, right, that light is a wave, or that light and electrons are waves, or this wave-particle duality? So really we're asking about electrons, but so why do electrons exhibit wave behavior? And so again, this was also going around in the 1800s, so kind of, with the birth of quantum mechanics, they were doing some experiments. And so I'm going to paste this picture. Oh my gosh, okay. I guess I won't paste that picture. But basically the first clue to this is, well, they thought, well, let's just shoot some electrons and through this double slit. And so we'll see what happens. And so if the electron is a particle, right, so let's imagine if you're throwing a baseball through this slit. So if we, and of course, right, there's a detector behind it. So here's our detector. And so the thought is, well, if it's purely a particle, we'll throw this electron through, and then it should, just splatter right directly behind it. And okay, well, let's see what happens. And so they did that. And so now let's redraw my crappy drawing. So experiment. And so except when they actually shot those electrons through the double split, they got this weird interference pattern. And I'll just show, I can try to draw it, but basically you get an interference pattern like this. So you have like strong bands and then repeating patterns where there's no light going through. So that's kind of weird. And so, right, that was showing them that, well, this is actually a wave. It's spreading out kind of a lot further than obviously a bowling ball just going through those slits. And then also the destructive interference pattern, as shown by the dark spots, shows that you have destructive wave interference. Then, of course, the bright spots are extra bright from your constructive wave. And of course, if I could draw this crappily, so you would have bands. So again, repeating of light and dark spots. And so again, that implies your destructive and constructive interference. I won't try to draw two waves. All right, so that was part of at least.
Are the double slits like on the same plane, or is it like one slit is in front of the other?
It would be like, yeah, on the same plane. So the idea is if they're just two bowling balls, they would not interact at all. They would make just two splats. But then they did interact, so that gives you the wave. All right, let's go back, and we're going to take a deeper look at hydrogen now. And again, talk about all the different transitions. And so your book does this pretty nicely. So I'm also showing Wikipedia. And so now this is showing now all the spectro series of hydrogen. And so your book, mentioned that. And so we'll go through them. So we have transitions in the UV. We have, of course, the ones that we'll see in the lab next week. But okay, well, what does this all mean? So let's take a step back. How do we even figure out what's what? And so again, we're going to our oversimplified hydrogen model. And so it depends kind of what approach you want to take. But basically we're saying, well, if we have one electron, right, what are all the possible transitions of it, either going from, right, our excited state to our relaxed state? And we could start, from our most basic. So we can go from n equals 2 to n equals 1. we could go, right, 3 to 1. So, of course, right, we could do this for every number. So 5 to 1, 6 to 1. So that would be a calculation. But then what if it goes in from higher orbitals, right? So we could go from n equals 3 to 2, 4 to 2. So all of these have a corresponding energy. And then basically once you find that energy, does it match to a line that we see? And so let's do that for one of the ones that we know. And so now I like to take the chemist approach to things. So let's try to calculate it. We'll get the data, then we'll verify it. And so now let's calculate the change in energy then for the n equals 3 to 2 transition. And so we might need to look back at our formula for that. And so there are also different versions of the formula, so now this would be a good time to bring up the other versions that your book has. So we looked at this formula, right? So this directly relates it to the energy. So this is just calculating the energy. But then we also had other formulas. Sorry. Oh, there we go. This is the one I was looking for. So often you also see this Rydberg-Balmer equation. And so this is useful just because then you don't have to do the conversion right from energy back to wavelength. This formula already gives it to you. So we have 1 over wavelength is equal to 1.097 times 10 to the 7th inverse meters times, again, our energy levels, so n initial squared minus n f squared. And so you'll notice I kind of throw these around back and forth. So right now I want to care about my transition. So we're looking at the relaxation, so higher energy to lower energy. But if you flip these ever, your number is just going to be negative. So it doesn't matter that much. So I don't care too much about the signs. It doesn't matter whether you put the 2 here or the 3 there. We care about the difference, right? And so if you get a weird negative number, obviously, right, we need a positive wavelength, so we can just figure that out. So let's see if you can calculate. Well, I wanted energy, but I gave you Rydberg-Balmer. So let's do both. So let's calculate our energy. So we can use this formula for that transition. And then I also want to know the wavelength that corresponds. Yeah. 3 to 2. So give me energy, give me wavelength. So does someone want to put up the board, at least whatever approach you took? And so again, I'm looking for either energy and wavelength. And depending how you're feeling, you could use either your energy formula for the transition to find the energy of the photon, and then plug that into here to get your wavelength. You could use the Rydberg-Balmer formula, get wavelength first, and then plug that into energy. So there's a lot of different approaches. So nobody wants to start us off on the board?
I think I can.
Yeah, just
I'm
go.
not confident in
And-
my math.
And it can just be whatever you solve for first, so there's no wrong way to start.
Alrighty, so I started with the Balmer equation. So I did 1.097 times 10 to the 7th times, I did 1 over 3 to the 2nd, because this is our initial orbital starting point, minus 1 over 4 to the 2nd, because this is our final orbital, and I got 1.52 times 10 to the negative 6.
I think you,
Does that make sense to anyone? Did I just do a bunch of chicken scratch?
I think you just did different, because I had said 3 to 2.
Oh, never mind. I did do it different then. It should be 3 to 2. I don't know why I wrote down 4.
I was going to say we could calculate it. We might want that later.
Who has a calculator that can tell me what this is instead of 1 over 4?
Ah, firing up my calculator. And so again, make sure you use your calculator during class so you can practice entering stuff. It's not always trivial. And so I always use the little E button so you don't have to write times 10, plus you'll screw up order of operations. Then just take the inverse of this. And of course, right, negative answer doesn't matter. We want a positive answer. And so we get our wavelength. So I'm going to convert it to nanometers. So times 10 to the 9th, which I'll do in my head, but I won't do it here. So 656 nanometers for this transition. And then, so that's our wavelength. And then does someone want to bring us to energy? Oh, I just did 3 squared and 2 squared. I was just, yeah. Yeah, I just didn't want to write that. I got a little lazy. Yeah. Yeah. Sorry? But it's 1 over your initial energy level minus 1 over your final. Oh, yeah. So that's 2.18 times 10 to the negative 18 joules times 1 over. So it's the same thing. And so again, this doesn't matter too much, your initial or final, but it's just more of a formality for our sake. So if we did 3 to 2, let's do that for energy right now. Oops, I'm getting squirrely here. So 1 over 9 minus 1 over 4. So now let's do that calculation. And notice, right, I just did the doubling already. So times my energy. So do we get, and then again, we want a positive answer. Or really, we care about the difference, right? So chemists care about the difference, physicists care more about their formalities, but again, we just care about our energy level difference, so I'm ignoring our sign. So 3.0, 3 times 10 to the negative 18 joules. And then what if we wanted to go back to wavelength, right? We could go back and forth. So let's throw it into this formula. So energy equals hc over wavelength. So let's go back and calculate this, right? We can either recalculate wavelength. So now I'm going to take my energy. So let's just do this before I get too sloppy. Yeah.
Just have a curious question. How come in chemistry we write the speed of light constant as a lowercase c, but in physics we write it as a capital C?
I have no idea.
Fair. Yes. Never mind. I was wrong. It's there is a lot. We at least cars.
It's negative 34th, right? So just solving, so I'm going to divide. So let me get rid of my weird negative. So divide by Planck's constant. Oh, 3 times 10 to the 8th here, sorry. I'll write that clear. So divided by speed of light. Oops. And take the inverse of that again. And so, right, we get our same answer that we did before. So we still get 656 nanometers for our wavelength. So do we feel kind of comfortable with that, with all these formulas, right? They're all telling us the same information. It's just kind of what form we want. Yeah. And so, right, we could plug this in to our formula here and kind of rederive, right, the Rydberg-Balmer essentially. So it's just a way so we can go all around.
Do you want the units to be in joules or added joules?
I have zero preference. Just as long as you label your units. So yeah, if you like using attijoules, go ahead, go for it. I usually just write the exponent, but I mean it's not a big deal. All right, so then what have we found too? Well, let's go back to our experimental data. So okay, great. We calculated this transition from 3 to 2. And so it turns out that this number, 656, matches with what we see as part of the visible series for hydrogen. And so again, you'll see this in lab. I thought about carting the tube, but then I was like, it's probably not that valuable. But right, you'll look at the tube with your spectrophotometer and then kind of see a red band that corresponds to this region. So of course, this has been measured, and then you could get this accurately. So I think in physics, this is an experiment you do with like the fiber optic cable, so you can hook it up to Logger Pro and like actually get this value. But I decided to, again, take the chemist approach where we'll start with the answer and then kind of verify it. Sorry. All right, so literally we could do this again. And so again, part of this is like literally figuring out every possible allowed transition and the line that corresponds to it. So of course, this already gets a little overwhelming. But we could calculate it for all the visible regions. And so what Balmer found is that all these correspond to transitions back to the 2 level. So a lot of these in the visible. So we calculated, right, 3 to 2, but 4 to 2, 5 to 2, 6 to 2, 7 to 2. Those give us kind of our main lines for hydrogen. But then what about all the other ones? And so all of these, again, exist theoretically. So I just kind of want to look at the Lineman series. Oops. Just because this is, again, kind of the first ones you would just think of. Well, theoretically, right, we could go 2 to 1, 3 to 1, 4 to 1, etc. But let's calculate either let's do the wavelength for those transitions. And then again, kind of see, yes, they are in that region. And let's do 5 to 1. And then does someone want to put this on the board so you can get here by any method you want? You can find the energy first. You could just stick it into the Rydberg-Balmer formula first.
Okay, I'm a little bit more confident on this one, if you want me to do it, if nobody else wants to.
Let's see, I'm not seeing anybody else leaping out of their seats, so I think you could go for it.
Erase for that kind of behavior. Alright, so I always start out my equations by writing what we're looking for here. And then I did 1.907 times 10 to the 7 multiplied by 1 over 5 squared minus 1 over 1 squared. Oh, you're right. Thank you. 09. You're right, I read it wrong on my thing, on my paper. And then I got,
You need that new calculation.
I don't think so. Test it, because my final answer was 434 nanometers. If that is correct, then I did it correct in my calculator. Cool. And that's what I got.
What do we get?
I got 434 nanometers for the wavelength.
Let me see. Is that what other people got? Yeah, so then this should be your answer with not a negative sign. And so that would make it like 94 nanometers. What did happen with your answer?
I am unsure.
That seems
No,
pretty
I did
far off,
I'm
though.
looking at it now. I did 1.097 times 10 to the 7th.
Calculator has those.
I hate calculator ghosts.
Yeah, always double check calculator. So always good. So right, at least if you can set it up, that's always, partial credit, especially for exams, and then always punching it in is more success. But yeah, you should have gotten like 94 nanometers. That's what I got. And then that's kind of what we were expecting, not to reveal it all away. But so this falls into what we call the Lyman series. And so, right, to figure this out, so you kind of did this on your homework potentially, but you can look up, right, the nanometers with the wavelength and then figure out what region it corresponds to of the electromagnetic spectrum. And so notice, right, these are pretty large, and so we kind of expect them to be higher energy, so that's why these are kind of in the UV region, so we can see that. And so again, these are just all our allowed transitions there. And so just to kind of keep going on, so again, right, just theoretically thinking of all the allowed transitions. So where do these fall in? So all these go from 4, or go down to 3, so 4 to 3, 5 to 3, 6 to 3, etc. So these are just called the Paschen series. But again, these are not in the visible region, so, but rather in the IR. And then this kind of makes sense. So again, we're thinking about as you get to those higher energy levels, they're closer and closer together. So relatively speaking, right, those are a lot smaller in energy, those transitions as they relax back down. So that kind of makes sense that they're in the IR region, again, lower energy. And then, so another thing to point out, because this probably comes up on your homework, So this is the energy, right, for one photon. So then if you start talking about like moles of photons, then you have to, kind of multiply or divide appropriately. So that may help you. Oh, so this is the energy for one photon. And so sometimes in your homework, it's like, what's the energy of a mole then a photon? So then you would multiply this by the mole. So maybe we should look at some homework, but I did want to point out at least like other elements and how it gets more complicated. And so of course, right, things get complicated since we can only solve or at least approximate the Schrodinger's equation for hydrogen, and then we can't solve for anything past it. And so I also wanted to point out that you get kind of funny things happening because of quantum mechanics. And so what this is showing here is actually helium has a bunch of different allowed transitions from two different possible states. And well, what the heck does that mean? And we'll appreciate how complicated things start to get. So now with helium, so it could be in two states. So of course it can have the 1s ground state. So this would be kind of the ground state. And then you'd be looking at every relaxation back to this ground state. So this is called the singlet. And singlet just means they're paired. And so going back to the picture that I'm showing from this pretty dense book, so that's what this diagram on the left-hand side is showing. So then somebody tried to calculate, all the transitions, trying to figure out what that might look like from all these orbitals. You can see they have S, P, D, and F kind of drawn out. So looking right 2s to the 1s right there is that transition. And I'm assuming this is in nanometers here, what they're reporting. At least that would make sense. Although now, admittedly, I'm not too certain.
It says it on the top right corner.
Yeah. Well, anyways, we just want to appreciate, right? So first of all, helium, you have every transition just from the ground state. So that's all of these. But then helium actually has another ground state shown there. And that's going to be what's called the triplet state. So now this is its other ground state. And then this will just kind of stays there. So this is kind of unchanged. And then every relaxation that you're looking at is transitioning from those higher ones back to that 2s, where you just had that lone electron on the 2s. So that gives you a bunch of other transitions.
So this graph here is, the left side is one of the ground states and the right side is the other ground state?
Yeah, which already gets like interesting and crazy and cool. But that's also, why we just kind of focus on hydrogen. But I at least wanted to show you kind of helium, and people do kind of work through these calculations and to try to figure out, because also what comes into play is trying to figure out those electrostatic interactions between the electrons and trying to figure out that Coulombic attractive forces. If you're interested, I could post a link to this book so you could, get yourself crazy. All right, I'll post a link to that.
Would an example of an excited helium state be 1s0, 2s2 then?
So helium, you said 1s0, 2s2. So for our purposes, I would be like, yeah, but because of what we said here. So this actually wouldn't be allowed based off of this
Okay.
information. So I'll put like, okay, for us.
Okay,
but, like-
it doesn't actually happen that way.
Yeah, but that goes back to, you know, like quantum mechanics and then like what you're actually looking at. Because, right, you're really, so let's go back to hydrogen. So other final thoughts. And so part of this is like, okay, yes, we can calculate literally every possible combination, but then when we look at it, what we're seeing, so like the most prominent bright ones are going to be the most frequent and the most, well, you know, they obviously have to be allowed, but basically the most favorable transitions are going to be brighter. And then you might have, you know, faint ones that do correspond to like funky ones that are higher energy and don't necessarily happen as much. So bright line happens, dim line, not as much. And again, right, you have to think about too, like what you're looking at, right? Because you have the gas of hydrogen, right? But then you're talking about just each excited state. So that's just like one electron getting excited. But then you have lots of hydrogen atoms all getting excited with different energies. So you're kind of seeing all of it. But yeah.
And then the black would just mean this does not happen at all on the spectroscopy.
Yeah, so if you don't have anything, then there's just no transition corresponding. And that goes into, you know, either it's not allowed by quantum mechanics or, you know, it just doesn't correspond to any energy transition. So let me pull up the homework. I don't have a physical copy on hand, so I'm trying to pull up Blackboard. Do you have other questions? Are we feeling somewhat better? I am watching the chat if anyone is there. Let's see. No, we didn't have any like I was talking about with the moles. All right, let's do this one. So let's say, oh, I don't like this question. Ah, there we go. Here we go. This is a better question. Oh my gosh. There we go. This is what I was talking about. Now, if I could just make that, I guess the screen is pretty large so you can see, but let me make that bigger. All right, so if our eyes, and our eyes are pretty cool, but eyes of a certain reptile pass a visual signal to the brain when the visual receptors are struck by photons of a wavelength of 850 nanometers. If the total energy is 3.15 times 10 to the negative 14 joules to trip this signal, what is the minimum number of photons that must strike the receptor? So see if you can figure that out. And then, does anybody want to put it on their board for us?
I can try.
Go for it.
So we're working backwards from, we were doing solar. Full energy is 5. I did not do this before. I was just like, I can do this.
So does someone want to help him out? So what equation?
What I did is I used the energy in terms of wavelength. So I set the energy equal to H times C over the wavelength that they gave.
So now we just, a lot of plugging in. And then, of course, right, this has to go back to meters, which,
Sorry, real quick, where did you get the constant?
so this is Planck's constant. So It was somewhere in the notes, but yeah, this is 6.626 times 10 to the negative 34. And then this is the speed of light, so we just round it to 3.
But isn't that,
What I did was I basically calculated that, and that's the energy of a single photon, right?
Yep.
And then I divided that total energy by the energy of the single photon.
That sounds excellent. So hang on, let me catch up to you with plugging this in so you can verify my numbers.
Make sure I didn't miss anything.
Yeah, and I could totally plug something in wrong as well. So divided by this. So then, did we get this for the energy of one photon? It should be around the negative 19th order. That's usually the scale. Is that what other people got?
I got to the 17th. That may have been my error, though.
oh, I see, I did not read it correctly.
Do we get this answer?
Is it supposed to be 8.50 meters, or times 10 to the negative 9 meters, or 850?
So I did 850 times 10 to the negative 7. You could do 8.50 times 10 to the negative 7th, though, too. However you did it. I was just feeling lazy, and I did what I call a lazy conversion. All right, did people get this? I was waiting for more thumbs up. All right, finally see some thumbs up. A lot of calculator questions. So, yeah, so just like you said, right, that was a key. So this is the energy of one photon. And I wish I could.
Yeah, I made a mistake on my conversion. I got a couple places.
Yeah, so at least we're seeing this as we're showing our work is important because it's easy to make a calculator error, but I will, of course, give partial credit. So right now this is one photon, and then, yeah, we had said that the total energy needed to retrip the signal was 3.15 times 10 to the negative 14th. So yes, we just had to divide to figure out, well, how many photons was that? And so let's see what we get. Again, it's making sure our calculator, punching everything in. And so I get this number, can't read, 1, 2, 3, 4, 5. So 1.3 times 10 to the 5th, roughly, photons. I'll round it to 3.5.
Yeah, that's the right answer. My first one was out.
So did we get that? Feel okay with that? Okay, sweet.
So the equation, the formula that we use is to calculate total energy or the change in energy?
So this is the energy, right, that corresponds both to the change in energy, right, but then that's the change in energy of one photon. So
Oh,
that's
okay.
that's both the energy, right, of the band gap of whatever your orbital difference that we're measuring is, right? But then that corresponds to the relaxation of one electron, which gives you, right, one little photon out there. Right, so again, this E that we calculate is whatever higher energy to our final energy, so that gives us some sort of corresponding wavelength that we see or that we don't see, right? If it's in the IR or the UV, then we have to detect it with our instruments and not just our eye. And then that's 1 photon. And then so to actually see it, I think what the human eye though can see like 3 photons or something crazy, I think. All right, I think that's a good place to wrap it up. Do we have other last minute burning thoughts? All right, so let's take our 10-minute break and then we'll go ahead and do the quiz then. And I will stop this stream.